Good morning, everybody. With the technical difficulties we had on Wednesday that stopped our share screen, it appears that it also affected our recording, so the recording did not go through. We will go through on Monday and review some of the material that was in there. A lot of it was review already, but I do want to push ahead today and get into more new material to make sure that we cover everything that's required so that you have time to study for the test that is coming up on Wednesday. So just that reminder that test 5, our last unit test, that is just the statistics unit. It is not cumulative. That will be on Wednesday, May 17th. And I will need to have that completed and submitted to me by 12:30 on Thursday, May 18th. So I will get that sent out probably Monday so that your people at your schools have it. If you would, and I'll make sure in that message when I send that out, I'll include a note that if you want to start early, you can start it on Tuesday so that you can get a head start on it to make sure you finish up in time to get it sent to me. This unit, I think, is a little bit easier. There's a lot of stuff in statistics, but we've only had about 5 lectures of it, so it won't be quite so bad for us. So it's a little bit shorter on this exam. So anyway, what I want to pick up with today is I want to look at these frequency tables that we had looked at actually at the end of last unit. Which is a way that we had used to organize data. For example, let's say that we're going to do a random sample of 100 students. And I will say 100 college students. And ask them how many classes they are taking currently. If they're taking 0 classes, we don't consider them to be a student at the time. So our frequency table is going to be number of classes. And then over here will be the frequency. In other words, how many students reported taking that many classes. So we have 1, 2, 3, 4, or 5 classes. And let's say we didn't have any students reported taking more than 5 classes. 10 students reported they were taking 1 class. 25 students reported taking 2 classes. 35 students reported taking 3 classes. 15 reported they were taking 4 classes, and another 15 reported they were taking 5 classes. Now, since this is online paper, I just put those little lines across there to help us keep track of things. So this frequency table could be, we used it in the last unit to make a bar graph, or even if it was categorical data, to make a pie chart or a circle chart. What we're looking at today is finding those measures of center and spread: mean, median, mode, standard deviation. So let's look at finding It's real funny. Let's look at finding the mode, first of all. That's the easy one. The mode is the number that occurred the most often. In this set of data, the number that occurred the most often is the 3. There's 35 of them. That's what the frequency means. Remember, what that frequency is telling us, the 10 for the ones is saying what we really have 10 ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 ones. And then we have 25 twos. Well, I don't want to write out all 25 twos, but you get the picture. And then we have 35 threes. We have 100 numbers here. And so this is just saying, well, there's only 5 different numbers. So rather than listing out all 100 results, let's just put the frequency with each of those 5 possible results. But it really is that long list. Well, so the mode is 3, because 35 people chose 3. Now, it's very important to list here. These are the numbers, 1, 2, 3, 4, and 5. A lot of people say if I ask for the mode, they'll say 35. Well, 35 is not the mode, it's the frequency of the mode. The number that occurred 35 times is the 3. Well, next we want to find the median. Remember, the median we had said was the middle number. And to find the median, we looked at finding the position of the median first. Now, these numbers are in order. There's 10 ones, 35 twos, or 25 twos, 35 threes. We can think of those being listed in order from 1 through 5. The position, since n equals 100 here, I could add these up, by the way, and that should add up to 100. It does. Since n equals 100, the position of the median is going to be at 100 times 1/2, or 0.5. Remember, it says the 50th percentile, which is 50. Since that is a whole number, that means it's between the 50th and 51st. So let's look up here. There are 10 ones. So this is 1 through 10 is right there. There are 25 twos. Well, the first 10 are ones, so that starts at 11 and goes through 35. So the 11th through 35th number, if I were to list these all out, 1, 1, 1, 1, 2, 2, 2, 2, the 11th through 35th numbers would be the twos. The 36th number starts out with the threes. 35 plus 35 is 70. So 36 through 70 in that list would be threes. 71 through 85 would be fours, and 86 through 100 would be the fives. Now notice when I'm adding here, I take the 10 and I add the 25 to get the 35 here for the top number of the next one. I took the 35, added this 35 to get 70 for the top number of that. All I'm saying is if I were to list these out, individually, all 100 numbers, the first 10 would be ones, the next 25 or 11 through 35 would be twos, the next 35 or 36 through 70 would be threes. Well, we want the 50th and 51st. Well, those are both in the 36 through 70 range. So 3 is also the median. The middle number here would be a 3. So now the mean is a little bit trickier to calculate. The mean requires a little bit of a process. We have to add these up. Well, there are 10 ones. So if I'm going to add those up, I would add 1 10 times. There are 25 twos. I would add the 2 25 times. So what we're going to do is we're going to multiply to add them up, basically. So if this is x here, and this is the frequency of x, what we're going to do is we're going to take the value x times its frequency. So 1 times 10 gives us a total of 10. 2 is the value times the frequency of 25 gives us 50. 3 times 35 gives us 105. 4 times 15 gives us 60. And 5 times 15 gives us 75. Now we add those all up. What do we get there? 0, carry the 1. 0, carry 2, 300. And we divide that, that is our total. And if we divide that by n, so remember it's the sum of the x's, well that's the 300. Divided by n, well n is 100. 300 divided by 100 is 3. So the mean here is also 3. So our mean, median, and mode all came out to be 3 for this list of numbers. The range, if we're looking for measures of spread, Well, the largest number is a 5 and the smallest number is a 1. That's just a range of 4. And again, we got that. 5 was our largest number, 1 was our smallest number. The standard deviation is a little trickier. So remember, the standard deviation, the first step is to find the mean. We already found that. The second step was those deviations. Remember, the deviations was the number minus the mean. So let's go up here and do the deviation. So here the number was 1. Remember, the 1 is our number. Minus the mean of 3 gives us a negative 2. This is a number of 2 minus the mean of 3 gives us a deviation of negative 1. The number was 3 minus a mean of 3 is a deviation of 0. 4 minus 3 is a deviation of 1. 5 minus 3 is a deviation of 2. Those are the deviations. The next step, step 3, was to square the deviation. So back up here, let's square each of these numbers. So negative 2 squared is 4. Negative 1 squared is 1. 0 squared is 0. 1 squared is 1. And 2 squared is 4. Now step 4 was to add them up, find the sum. Well, just like with the mean, however, when we went to add them up, we had to take into account that there were 10 1s, so we had to do 1 times 10. There were 25 2s, so we had to do 2 times 25. Similar thing happens here. We have a deviation of 4. The deviation of 4 comes from the 1s. Well, there's 10 of those. So we have to do 4 times 10 to get 40. The deviation of 1, or the squared deviation of 1, is associated with the 2s. There's 25 of those. So 1 times 25 is 25. Deviation of 0, well, there's 35 of those. It's still going to be 0 times 35 is 0. Another deviation of 1 times 15 of those is 15. And a deviation of 4 times another 15 of those is 60. And now we total those up to get that step 4, which was the sum. Oh, what is that? 140, it looks like. That is our sum of the squared deviation. And then we divide by n minus 1. So dividing by n minus 1 here, n is 100. So 100 minus 1 is 99. So we're going to divide by 99. So 140 divided by 99 is 1.414. Remember, that had a name. That was the variance. To get the standard deviation, we had to do a last step. That was the square root. So the square root of 1.414 1.189. That is our standard deviation. And remember that standard deviation is telling us, on average, how far is each number from the mean? Well, I mean, the mean is 3, so we have 1 is 2 units away, and 2 is 1 unit away, 4 is 1 unit away, 5 is 2 units away. But most of the numbers, there's more numbers in the 2 and 4 than there are in the 1 and 5, so it makes sense. Yes, it's just over 1 unit away is the average distance from the mean in this data set. So a standard deviation of 1.189 makes a lot of sense. We will come back and do more examples of finding the mean, median, and mode, and standard deviation for a frequency table like that. For now, let's move on to the next subject, which is probability. Probability is basically describing how likely it is that something will occur. Now, it's important that we stress that something will occur. A lot of people misuse probability and say, what's the chances that this happened? Well, if it already happened, probability doesn't apply to it. Probability is looking for a future event or an unknown event. Once it has happened and the result is known, probability no longer applies. There are a couple of different thoughts on probability, versions of probability. Mostly, we use what's called a theoretical probability. Sometimes called classical probability. And what that is the probability of an event occurring. So X is the event, say the desired event. The notation P of X is the probability that X will happen is equal to the number of outcomes containing X over the total number of outcomes. So there's some vocabulary to define here. So we have outcomes. Are a result of what we call a random experiment. An example here would be rolling a die. A possible outcome could be rolling a 1, or a 2, or a 3, or a 4, or a 5, or a 6, because those are the possible results of rolling a die. Now, sample space is a list of all possible outcomes for that random experiment. Which is what I actually just gave you right here. This is the sample space for rolling a die. That is all the possible outcomes or all the possible results for that experiment. Results here. And so then an event, and I misused the words a little bit up above here, is just one or more outcome. So an example here, I could have rolling a 2. That would be an event. One of the outcomes of rolling the die is a 2. But I could also have an event that was rolling an odd number. So the results here would be a 1, a 3, or a 5. Those little squiggly brackets are what we use to list the outcomes of a random experiment like this. So that contains 3 possible outcomes. The event of rolling an odd number could be any of those 3, a 1, a 3, or a 5 of rolling that die. So the probability of rolling an odd number on that die there are 3 odd numbers out of 6 total possibilities. That's 3 out of 6, or 1/2, or 0.5 probability. The probability of rolling a 2, well, there's only 1 2 on the die out of 6. So it's a 1 out of 6, or a 0.1667 probability. Now, a little bit more, a little less contrived example here would be, let's throw marbles in a box. Let's put 4 red and 6 blue marbles in a box. Then we close the box up so that we have a hole that we can reach in and grab a marble, but we don't actually see the marble until we've pulled it out of the box. We have to assume all the marbles are the same. At least to the touch. Obviously, they're going to be a different color when we pull them out, but that is the only thing different. When we look at them, they're the same weight, same texture, same feel, same shape, all perfectly round, all smooth, whatever, so that we can't feel the color when we're looking in that box. It truly has to be what we call a blind draw. We have no way of predicting until we pull it out and look at it to see what color it is. So here, the probability, so our random experiment is going to be drawing out a marble. The probability that that marble is red, well, there are 4 red marbles out of 10 in the box. 4 out of 10, or 0.4, is that probability. Probability of drawing out a blue marble. There are 6 blue marbles out of 10. So 6 out of 10, or a 0.6 probability. So it's really that simple. It's a matter of counting how many marbles meet the condition we want out of how many total marbles are there. So let's look at a little bit more complex experiment. We're going to draw out 2 marbles. However, this experiment seems simple, but there's more to it than that. There's 2 possibilities. Possibility 1, we draw 1 marble, then replace it before the next marble is drawn. We replace it and randomize. Randomize is just a fancy way of saying mix them up for the next draw. So what does that mean? Well, it affects our probabilities. So if I want to find the probability of drawing a red marble followed by another red marble, I'm just going to use R for red. So red and then red again. This is equal to the probability that the first one is red times the probability that the second one is red. Well, the first one being red, there are 4 red marbles out of 10 in the box, so 4 out of 10, or 0.4. For the second one being red, well, since we put the first one back in, there's still 4 red marbles out of 10 in the box. So it's still 0.4. So that's a probability of 0.16, or 16 out of 100. This is called with replacement. If you were to get into more advanced statistics, binomial probabilities are a huge one out there. It's probably the second biggest one next to normal probabilities. Binomial probabilities, in order to work, demand that there be replacement. So the second possibility draw both marbles at once. Now, for the sake of analyzing the experiment, we're going to look at one of them first and then the other. We can't look at both of them at the same time because really it's impossible to analyze that. So now the probability that both marbles are red is once again the probability that the first is red times the probability that the second is red. That has not changed. But now the first one being red, there's 4 red marbles in the box out of 10, so 0.4. The second one being red now, however, this first one was red, there's only 3 red marbles left in the box, and there's only 9 marbles. So we drew them out at the same time, but we consider the first one to come out first, then we consider the second one being pulled out. The second one is only 3 red out of 9 total in the box. That probability has changed. 4 times 3 is 12, 10 times 9 is 90. This is now 12 out of 90. 3/9, of course, is 0.3333. 12 out of 90, or 0.1, what is that, 27? No, 1333. So that comes out to be. So notice it's a significantly different probability. With replacement, it was 0.16. Without replacement, it drops to 0.1333. Well, that's because this was a small population. There's only 10 marbles in the box. Only 4 of them were red. So taking one of them out before we drew the second one drastically decreased the number to choose from. Now, a question that comes up here is, well, how did we know that the first one was red? How did we know there's only 3 red ones in the box? Well, we didn't. But if the first one was blue, it's over. We can't get both of them red. So we had to assume, before we analyzed the second marble, we had to assume that the first marble was already red, or we would have been done. There was no reason to look at the second marble even if the first one was not red. So there's a step from there then where we get into more complex probabilities. Here there's only a couple of possibilities is what we analyzed, but if there's more than one or two, or more than a couple probabilities, one possibility doesn't give us any probability there. It's a guarantee. But if there's more than a couple of possible outcomes or possible events, we often list them in what's called a probability distribution. Get back here. And all a probability distribution does is much like a frequency distribution. It lists all the possible results and then the probability of it. So let's look at number of siblings. So what we're going to do is we're going to just look at the number of siblings that have students in our school. So we've developed a larger probability where we know what these probabilities are. And so what we're looking at here is if we randomly select a student from the school. The probability that student will have 0 siblings. So what I'm going to do is I'm going to list it like this. We're looking at number of siblings. X equals the number of siblings. So our values are X, and then we're looking at the probability P of X. So the probability that that student has 0 siblings, in other words, they're an only child, is 0.18. The probability that student has 1 sibling, 0.43. So a family with 2 children. Probability that there's 2 siblings. They have 2 siblings is 0.27. Probability that they have 3 siblings, 0.09. And the probability that they have 4 siblings is 0.03. Now again, for the purposes of this experiment, this example, we're assuming nobody has more than 4 siblings, no families with more than 5 total children. So it lists out each of the possible values of the random variable, anywhere from 0 to 4 siblings, and then the probability that each of those will occur right here. Now there's a couple of conditions that must be met. It's the probability of each value has to be at least 0 and cannot be more than 1. The probability is 0, that means it's impossible. If the probability is 1, that means it's guaranteed. Well, nothing is guaranteed in life unless there is only one option. So it's impossible to achieve a probability of 1 unless something has already occurred. The second condition is the total. Remember that symbol means the sum of all the probabilities of P of X's has to add up to 1. So if I add these all up here, what do I get? 61, 88, 97. Yes, that adds up to exactly 1. So that's perfect. Total probability of 1. So this is a valid probability distribution. Now let's ask the question. If we randomly select a student, what is the probability that they have exactly 2 siblings? So this is probability that X equals 2, that the random variable X is 2. Well, here, we just come over here, we read it right off the table. That's 0.27. What's the probability? I'm going to abbreviate here. Probability that they have 1 or 2 siblings. Again, we read those right off the graph. 1 is 0.43, 2 is 0.27. So we just add those together. 0.43 plus 0.27 equals 0.70. Now a note here. Above, when we were drawing out the marbles, when we drew 2 marbles, we multiplied the probabilities. That's because we needed both of the marbles to be red. We needed both. We had 2 chances, and both chances had to meet the condition. Here, we only took 1 chance, and we had 1 of 2 conditions, either 1 or a 2. That's why we were adding the probabilities there, because we were only doing 1 student, but there was 2 different conditions that they could have met. So we add those probabilities together to get an increased probability. How about what's the probability that they have at least 2 siblings? Well, at least 2, that includes 2. So I'd be adding these up. So that's the 0.27 plus the 0.09 plus the 0.03, which adds up to 0.39. Now here's a subtle difference here that often confuses people. What's the probability of being more than 2 siblings? Now this no longer includes the 2. 2 is not more than 2, so it's just the 3 and the 4. That's the 0.09 plus the 0.03, which is a 0.12 probability. So you can see this here, at least 2, it included the 2, more than 2 did not. Here the 2 is what we call a boundary value. Boundary value separates the values that we want from the ones we don't want. We talked about this a little bit in Unit 4 when we were looking at representing numbers on the number line. The difference between x equals 4, x is less than 4, or x is less than or equal to 4. The boundary value of 4 is either included or not included, so we had that closed dot or that open dot. Same is true here. The 2 is not included when we say more than 2, so we only had to add in the 3's and the probability of 3 and the probability of 4. At least 2, however, the 2 is included, so we had to add in the probability of 2, 3, and 4. Let's look at probability of being less than 3. Now again, this does not include the 3. So that's 0, 1, and 2. That'd be 0.18 plus 0.43 plus 0.27, which is a total of 0.88. Compared to the probability that x is less than or equal to 3. Well, now that is going to include the 3, so that goes all the way up here. So 0.18 plus 0.43 plus 0.27 plus the 0.09 gives us 0.97. Now I could have, since I just added up all the way from the 0 through 2, I could have just added the value for 3, the probability of 3, which is the 0.09 to this, to get the 0.97. But I wanted to do this example here because it brings up a great concept in probability, which is called a complement. The complement is everything else. Everything that is not in the probability. So what do I mean by that? Well, the probability of being less than or equal than 3, that included the probability of being 0, plus the probability of being 1, plus the probability of being 2, plus the probability of being 3. The only thing that it not included was the probability of being 4. Now, since we know that all these probabilities add up to 1, we could use that complement. The probability of x is equal to 1 minus the probability of the complement of x. So here, instead of adding up all 4 of those probabilities, what I could have done is I could have said the probability that x is less than or equal to 3, which includes 0, 1, 2, and 3, is 1 minus the probability that x equals 4. So 1 minus the 0.03 gave us 0.97. So that would have been a lot quicker way. Now with only 5 options, 0 through 4, it's okay to just go ahead and add up those other 4 options. But let's say this was 0 through 20, so we had 21 possibilities. If I wanted to know the probability of being at least 1, I'd have to add up probability for 1, probability for 2, probability for 3, all the way up to the probability for 20. I'd have to add 20 probabilities. Or I could have just done the probability of 0 as the complement, did 1 minus the probability of 0 to get that probability. That's not something we're going to test in this course, that idea of a complement, but it's a very handy tool that if you do go on to any more advanced statistics, very handy tool to keep in mind. Finally, we have the concept of a contingency table. What a contingency table or a two-way table does, it takes one set of data and it looks at 2 different characteristics or 2 different variables of that data. So let's say that we are going to randomly select 1,000 college students. And from those students, they are in one of 3 programs. The tech college, we only have 3 programs. We have tech diploma programs. We have associate degree. And we have liberal arts. And then we want to look at age groups. So we're going to look at students who are less than 30, students who are 30 through 39, or in their 30s, and students who are 40 or greater, 40 or older. And of these 1,000 randomly selected students, 263 were tech diploma students that were less than 30 years old. 148 were tech diploma students that were in their 30s, and 19 were tech diploma students that were 40 or older. Of our associate degree students, there were 208 associate degree students that were less than 30, 201 that were in their 30s, and 51 that were 40 or older. Liberal arts transfer, we had 78 that were less than 30, 26 that were in their 30s, and 6 that were 40 or older. Now, to make a contingency table work, we need some totals. So let's do row totals. So if I add up this top row here, what it looks like, I get 549. This next row looks like I get 375. And the bottom row, I get 76. There's my row totals. I also need to do my column totals. So let's see, this first column looks like it has 430. This next column looks to have 460. This last column has 110. Then we have our grand total here, which adds up to 1,000. If I add these up or these up, I should get 1,000 total, and I do. I'm going to refer to that as my grand total. That is the total number of students that we have in this sample period. So now if I want to look at, if I randomly select a student, what is the probability that that student is a liberal arts student? I'm just going to do LA for liberal arts. Well, here we're just looking at the totals. There's 110 liberal arts students out of 1,000 total. I could divide that out. Get 0.11. Now, if I want to know what's the probability, come on, that randomly selected student is in their 30s, 30 to 39. Well, look over here. I have 375 out of the grand total of 1,000, which of course is 0.375. Well, those probabilities aren't very interesting. We can find those pretty simply. So let's look at combined probabilities. Let's look at the probability that a student is 40 plus and an associate degree. Let's do associate for associate degree. So it has to meet both of those qualifications. So here are the students that are 40 plus. Here are the students that are associate degree. We only care about the ones that are both, those 51 there. There's 51 out of 1,000 total. That's a 0.051 probability. So, and remember, it had to meet both conditions. So it has to be both 40 plus and associate degree, which is the 51 students. We might say, what's the probability that they are 40 plus or their associate degree? Now, it's the or, it just has to meet either one of the conditions. So here are the ones that are 40 plus. Here are the associate degree. You just have to meet either one. So we're going to add those up. Be careful that we don't add the 51 in there twice. We can only add that in once. So we have 208 plus 201 plus 19 plus 51 plus 6 out of 1,000 total. So if I add those up, what do I have there? 485, it looks like, out of 1,000, giving me 0.485. So the last thing I want is, what if we know something about the result already? This is what gives us what we call a conditional probability. Because we know something about that result, it narrows down our size, so we're not looking at the whole group anymore, we're just looking at a piece of it. let's see, what's the probability that a student is 40 plus given they are associate degree? So the key word here is given that they are associate degree. If we say that we're given that they're an associate degree student, that means we're only looking at the associate degree students anymore. We're only looking at these students here. We have 51 that are 40 plus, only out of the 460 now. We're not looking at all 1,000 students because we already know that this student is an associate degree. So we're only looking at the 460 associate degree students. So this probability becomes 51 out of 460. Which gives us 0.1109. Is that probability? Now, one that a lot of people would think would be the same, but it's actually very different. What's the probability that the student is associate degree given that they are 40 plus? So before, we knew that they were associate degree, so we're limiting ourselves to those that were associate degree. Now we know they're 40 plus, so now we're looking only at those that are 40 plus. Only at the 76 that are 40 plus. Of those, 51 are associate degree. So this is still 51 students, but only out of 76 that were 40 plus. 51 divided by 76 is 0.6711. Notice those are very different probabilities. We're still looking at the same students for our included group, but the total that we're selecting them from is much different because we're looking at different conditions. Here we knew they were associate degree, so we're only looking at the 460 associate degree students. Here we knew that they were 40 plus, so that meant we were only looking at the 76 students that were 40 plus. Okay, with that, that is it for the day. I've actually gone a couple minutes over, but that's okay. It'll just be the recording today anyway, it looks like. With that, you guys have a great weekend, and hopefully we'll see you all on Monday. Monday, there will be no new material. It's just going to be reviewing of everything for our exam on Wednesday. Have a great weekend.